All right. Hi again. So before we even get started, just wanted to say thanks for hosting us.
Of course.
This is, very great. We are happy that we can share a few bits about Ray and Anyscale. So there is two of us, me and Amy. I am technical training lead. Amy joined me today to present that hands-on part. And we are joining here in person, but we have an excellent lineup of TAs that is really a mix of engineers, AI educators, and solution architects. So throughout this tutorial, if you will have any questions, just feel free to ask them directly in the chat, and you will get your questions answered by our TAs team. So let's jump right into it, right to the plan. We divided the whole session into few smaller sections. After each section, we are going to do some small QA session so that everybody will be invited to unmute themselves and ask any questions live. But again, throughout this tutorial, feel free to ask the questions directly in chat. If you run into some troubles, also ask them in chat, and we'll just make sure to help you. So to start with, we will do some lightweight introduction to Ray and Anyscale to give you some mental model or frame, what kind of tool it is, the open source project, as well as the platform. Then I will do short tour directly in the Anyscale platform. I will present some clusters and workspaces. So we'll focus a bit more on the development stage of the machine learning model lifecycle. After that, Amy will take over and present example use case, example workflow that will be fine-tuning NLP model, text generation model. So that will be distributed fine-tuning, hyperparameter tuning, and the batch inference with a lot of tips how you can effectively distribute that from the single machine to the full cluster. And I will conclude with Anyscale jobs. So we will visit a bit that production stage of the machine learning model lifecycle when you are running the production jobs in as a standalone on the standalone clusters and you delegate some compute there. Okay, I believe that we went through the course logistics just before this section, so I will just skip that. You should see something like this essentially in your cluster once you logged in. So just feel free, make sure that you have this tab opened, as we will visit that place many times. So I'll just skip that and jump right into introduction to Ray open source project as well as Anyscale platform. So high level observation that is more and more apparent is that AI or ML applications need more and more compute. That hunger for more compute to train or fine-tune or serve the models grows really fast. So our rough estimation, looking at the historical data, is that it is approximately 2x every 3.5 months. This is because the size of these models grow, but also complexity of ML pipelines grow too, so that to keep up with this pace of development, you have no other way than distribute your workloads into multiple GPUs, multiple nodes, multiple machines. As the progression of the CPU and GPU capabilities simply do not keep up with the demand of the compute. So this is some sort of a background observation that is more and more apparent these days. So these two guys actually back a few years ago worked on their PhD thesis at UC Berkeley, Robert Nishihara and Philip Moritz, and they started this Ray project. So what initial problem that they had was, hey, we are running a lot of ML research experiments and we really need to run it on multiple nodes and multiple machines. So how we can do it? So that was the initial motivation, and back then you didn't have, say, user-friendly Python-first tools for distributed machine learning. Of course, you have OpenMPI and specialized C-based tools, but they are not easy to program with, your pace of development is not that high. So fast forward to today, Ray was adopted widely by, broadly speaking, AI community, with more than 800 contributors to the open source project, and a lot of meetups and events focused around Ray around the world. So this is both North America, South America, China, Europe, and other locations as well. So we also observe great adoption of Ray among many successful companies. And the common denominator is that all of these companies have machine learning pipelines and run models in production, and they need to have scalable compute framework to just handle distributed model training, fine-tuning, and serving. So, and these companies include like Riot, Spotify, Uber, ByteDance, and others. So if we say zoom in into a few example companies and what they are doing with Ray, one example is Uber. So perhaps some of you just get here using Uber, and the part of their user experience is accurate ETA prediction. So the better is the ETA prediction, the better experience their users have. And they are actually using Ray for both a deep learning and classical machine learning, and to train this model and run hyperparameter tuning at large scale so that they can drive better accuracy of their ETA and maps and marketplaces. Moving on to the Instacart, for them, what matters is, again, the delivery ETAs, but also the order fulfillment and scheduling. So they used Ray to train a lot of models in parallel, and they sort of squeezed the time required to train 12K models from days to hours, thanks to the capability to train multiple models at the same time in parallel on the cluster. So thanks to that faster retraining logic, their fulfillment and scheduling and ETAs are more accurate, which translates into their business. Quantum Black from McKinsey & Company uses Ray to run simulations. They designed sailboats using simulations, and they used Ray to scale their simulations. And they won the America's Cup with their sailboat. And the more recent examples touching current trends in LLMs and Gen AI comes from OpenAI. So they use Ray to train their largest models, including ChatGPT, GPT-3, and others. And they use that as a tool to scale, in their case, to the extreme scale of the training and fine-tuning of their models. Now, those are just few particular examples how companies use the open source project to scale their machine learning workloads. But if we sort of zoom out a bit to the LLM pain points in general, so touching that recent trend, there is really, say, three typical problems with that. First one is that training at the large scale is usually expensive, as you need a lot of GPUs and a lot of compute. Second problem is that your favorite tools might not work at this scale. So scaling from the single workstation to the full AWS cloud and run the distributed training is not a straightforward task. Finally, with this fast development of new AI techniques, you actually want to iterate very quickly and iterate very quickly at this large scale, which also poses certain challenges. So we see Ray as a potential solution that can help you solve these problems. So one of them is that you can very easily use the spot instances with Ray, which will drive the cost of training and fine-tuning down. Then the flexible scheduling and auto-scaling allows you to actually dynamically assign compute resources like GPUs and CPUs to some particular parts of your machine learning model lifecycle, but also with auto-scaling, you can scale up and down your cluster according to the needs that you have at the moment, which means that you can start with a smaller cluster, and once you want to start your large-scale LLM training, Ray will scale up your cluster to just provision enough resources to facilitate this training, and right after we'll scale this cluster down to essentially save you cost of running this large cluster. And at the end of the day, Ray open source is just a Python library, so that it basically fits your existing ML Python stack. And in this way, you can very easily integrate that with your existing tools, and that will increase the pace of your development.
Excuse me, someone asked a question.
Yeah.
We already do the checking pointing when using the spot instance.
Yeah, so how it works is that when you are using spot instances and some spot instance is terminated, that compute will be restarted, and Ray basically see that some spot instance is terminated, so we'll provision you with the new instance. And now, speaking about the Anyscale platform, you can actually choose whether you want to use on-demand instances or spot instances. Mm-hmm. Another option is that you can actually set that, hey, I want to try with the spot instances first, but if they fail, I want to sort of roll back to on-demand.
Can we choose like how many jobs, like what's the percentage of the jobs using the spotted, and how many use the dedicated?
No. I mean, when you work with a single cluster, you work with this amount of resources. So with Ray, you don't need to be worried how many nodes I have, or where should I schedule my particular parts of the model training. So Ray basically does this for you.
So for your resource allocation, scaling, and it's scaling for a parallel training for multiple models, or is scaling for just a single large model?
Yeah, both. Yes. So in our hands-on session today, we'll actually have a closer look at the data parallel approach, which means that you have copies of your data on multiple machines. You shard the data set and you run the model training. So essentially, you have a larger effective batch. Yet, you can use Ray to run model parallel approaches too, meaning that your model is so big so that it doesn't fit into a single GPU. So you need to load it 16 GPUs and then train this model, which is inherently distributed across multiple GPUs.
Cool.
And the third approach is that, hey, I have, say, time series forecasting data, so I want to train 1,000 models at the same time, say, per user, per location, and yeah, this use case is also supported. We can share examples.
Cool.
Yeah.
Thank you.
And do you expect all the data in one place, or can you do federated learning?
Yeah, so you can actually load the data from multiple S3 buckets.
But can you split on premises and S3 and multi-cloud?
I mean, in principle, you can do it, but you will need to implement this logic
Manually.
Yes.
And when you say implement it manually, are you going to pull it from all those sources and put it in one place, or are you doing genuine, you move the model to where you're training that particular segment? Like it's not sharding, right? Because you shard data, you don't shard models, right? So the real question is, can you do federated learning?
So the federated learning, my understanding of that is that you delegate model training to some remote edge devices.
Yes.
Then you sort of have a
and
sync.
then you have a parameter aggregator, for the lack of a better word. You probably know the right word, but yeah.
The server, like a parameter server that aggregates those weights.
Okay. So I see two cases here. Mm-hmm. So first one is that if you want to run this federated learning and train the models on edge devices like smartphones and others.
Let me give you a better, more practical use case. So let's say that a number of banks want to consolidate their threat detection models, but they don't want to share client data, right? So they'll use federated learning to move the model around to all those different banks, but one of the banks or one independent, like an auditor, would host the parameter server for that situation. I think
Okay.
that's horizontal federated learning or vertical.
It's
Yet you
horizontal.
are
Yeah, horizontal.
you are training the same model,
Uh-huh.
or
yeah,
you are
same
training
model.
different.
One model. Yeah, there's a threat detection model. Yeah.
I see. Okay, so it's like training model.
I mean, no's a
in some
fine
area.
answer, but I
Yeah,
just
yeah, sure. I'm
yeah.
trying to understand the use case. So you are
Uh-huh.
training the model in, say, one network or on one data set, then you actually move the model.
Well, everyone has a different data set, and and they don't want to share aspects of that data set, right? But they do want what the features that are required to do threat detection in this particular use case. I mean, it's a real use case.
Yeah. So I think that this will require multiple ray clusters, say per location, and then you will just need to move the model checkpoint from like one location to the other. In this way.
But it doesn't really manage it for you.
No.
Okay.
In
that's
case,
fine.
In case of like
it's a special use case.
that
and
would
it's
be
a
custom use
sort of,
case.
No worries. Just wanted to check because of
Sure.
sort of the general descriptions, sort of implying maybe it does. That's the only reason I asked. But let's keep moving.
Sure. Just to like clarify one thing, if you opt in to run the parameter server and the workers that train the model, you can like easily express this one, this architecture, like within the single cluster. So it's like a shared data.
I see.
For it.
Yeah, that makes sense.
But in your case, you will need separate clusters.
Right. That makes sense. That's clear.
Okay. All right. So all of those like examples and use cases that we mentioned, they really have a common denominator, so that the approach for Ray is that it should be Python first. So it is at the end of the day just a pip install Ray kind of situation, Python library. That simple and flexible API that speaks to machine learning practitioners and data scientists. So the whole philosophy is that to run your ML workloads at scale, you should not be like a distributed systems engineer, or you don't need to have this specialized knowledge how to manage the cluster, how to handle with fault tolerance, how to handle communication across the nodes and stuff. So the API speaks to data scientists and they have familiar terms in the API. Scalability that comes sort of with Ray by default, scaling from laptop to Buffy workstation to the whole AWS cloud situation. Finally, support for heterogeneous hardware. This is really important as we see that some use cases require GPU instances, some other require like CPU instances, but there's like a bunch of use cases where you actually need the mix of CPU and GPU instances, and Ray supports that. And the custom
and I guess the
hardware too.
question there, have you used Trainium yet? Which is our GPU, the Amazon GPU?
I'm not aware if, I mean, I didn't try personally. I'm not aware if we are running some internal project, but I'm happy to like follow up on that.
Yeah, let's follow up on that.
Yeah,
because,
sure.
Because Intel has its own GPU. I mean, there's a million GPUs out there, it seems, besides NVIDIA all of a sudden.
Yeah, let's follow up on this.
Sorry.
Currently there's ARM-based. Ray has support for ARM-based processors like the NVIDIA A100 on AWS. But we can try to run Ray on Trainium, but that's not officially supported yet.
But that is our PSA.
Okay.
Dedicated to
we know each other.
so.
Oh, good.
Okay. All right. Let's move on. So we mentioned few different use cases, but what is actually important for data scientists or ML practitioners is that you can express the full machine learning lifecycle, the full application that starts with like data ingest and pre-processing, training, tuning. Once you have this trained model, you actually want to do something with this model downstream, which usually means two things. First is offline or batch inference. So you have your model somewhere and you want to run the job maybe on a regular basis and you want to just run inference on some large data using this model. Another case is online inference, serving model in the production environment and serving online inference pipelines right in production. So what Ray can do is that with Ray you can express this full application lifecycle using the single compute layer, which is Ray. And because it's just Python library, at the end of the day, you can actually integrate that with your favorite tools, like weights and biases for experiment tracking, or like PyTorch, Hugging Face, and others. So it basically will fit into your existing Python stack.
Yeah. PyTorch Lightning.
Yes, absolutely. All right. So all of that traction and excitement about the Ray open source was a initial motivation to start a company co-founded by PhD researchers at Berkeley. They were advised by Jon Stojka back then. So just wanted to reiterate on those three trends that we see, that computational demands in AI are growing, and they are growing faster than yesterday, basically. Then we observe the end of Moore's law. So meaning that existing accelerators like CPUs, GPUs, and specialized hardware do not keep up with the demand. You have no way, you have to distribute across multiple nodes. And the third one is that, very apparent for us, is that AI and ML use cases are becoming more and more popular in multiple verticals. If you think about the logistics, e-commerce, retail, healthcare, and others, you see the growing demand of AI and ML use cases, and tooling to both experiment with machine learning models and both train them and serve them in the production. So Ray and Anyscale, if we look at the relationship between these two entities, is that Ray is that open source, unified and scalable tool to run your machine learning applications. And Anyscale, our vision for it is that it is the best way to run Ray applications, run Ray servers. So it is fully managed service. It gives you both development and production kind of experience. And actually you can move from development to production within a single platform, which can be very useful or powerful in case you are running some complex pipelines and you want to move that somehow to the production environment. Anyscale comes with a bunch of productivity tools and also observability that makes data scientists, machine learning practitioners more productive. And yeah, so to conclude that intro, more applications need to scale. Our vision for Ray is that this is unified framework for scalable ML, and Anyscale is the best platform to run Ray applications. At this point, I am going to switch to the Anyscale UI, but if you have any questions now, it's like the good moment.
No, I have a just very might be tricky. Just one thing, like we already have like this part for this distributed computing. So what's the difference between Spark
And just, I hate to interrupt you, but your voice is coming in very garbled. Maybe move your mouth closer to the microphone or something like that.
just
I don't know what he said, but I think it was maybe about how the camera is off,
Oh, you have to turn the camera on your side.
like for this room.
Yeah, but I think when you plug in there, it starts coming through.
Yeah, we turned off my audio and video because we had this
Oh,
echo.
right. Yeah, but I think that was
is
audio
it better
only,
now?
not video.
It is better now.
Yeah, much
Okay.
better.
Okay, thank you. I removed my headphone actually, so maybe that might be the reason. Yeah, so might be a very like silly question. I'm not sure, but like we already have like Spark for the distributed computing. So what's the difference we can say in terms of Spark with the Ray? Like,
I believe that the question was about the Spark versus Ray. Is that the question?
yes.
Okay, yeah, makes sense. Right, so the vision of these two libraries are different. What I mean is that Spark is for data processing at scale. It is for ETL. So if you have use cases and workloads that requires this kind of tooling, go with Spark. Now, if you want to do this, what we call last mile data preprocessing or data ingest, essentially morphing your data so that it can be fed into the model for model training or fine-tuning, this is the moment when Ray is an option for you. And Ray is focused on scalable machine learning, and it is not focused on data processing or ETL type of workloads. So
But
that's
we have
the
Spark ML also for the like train the model. We already have Spark ML. So I'm no, I'm just, maybe you're right, but I'm just clearing my doubts actually. We have Spark ML also. So if what's the difference with, because we on the Spark ML also we can train the model, so we can do all the train the model. So what's the difference in that way?
Yeah,
I can understand what you're saying, and I think it's accurate, but I think what I'm hearing him say is a little bit different, right? Because, yeah, you can create these pipelines in Spark that do ETL, but they also train the model, right? I mean, that's also part of
Yeah,
it.
so the ML component of Spark, so how we might be different is that indeed you can train ML models using Spark, yet it is really matter of focus. So with how I see Ray is different is that our focus is only on the scalable ML. So you can really express arbitrary training, fine-tuning logic using Ray. What it means is that it is not only like standard cross-validation with XGBoost, but if you say want to go with more complex logic like multi-stage training, so first training session on XGBoost, then fine-tuning that on the data that comes in a bit later, and you need tools to express this, I would recommend to try Ray for this type of logic.
Okay.
Especially
Okay.
if you have some stages that require larger cluster and some other stages that require smaller cluster, that autoscaler that comes with Ray might be useful to you.
Okay, I got it. Okay. Thank you. Thanks.
Thank you. Yeah.
Okay.
Do we have other questions? If not, I can just...
Yeah, and for some reason I can't get the camera to work over there. I just pushed the button a couple times, but it's
I
just
see. Okay.
video is off, video is on, but there's no picture coming, so I don't know what to say.
All right. Okay. Sorry that you cannot see us, but you can see the screens.
But turn your video on, just to see if somehow that.
Let's try it for sure.
Still here?
Oh.
Like
Yeah.
this?
Yeah, that's better.
Yeah, both of them.
That's better.
Okay, that's great. Nice. Okay, so let me continue. So what I'm going to do now is to give you a very brief introduction to Anyscale, and we will have a look at a few components. So again, when you look at Anyscale from a distance, it is the platform that manage Ray clusters and Ray applications for you, and you can combine both development and production needs within the single platform. What I mean here is that for development, you have tools like clusters and workspaces, so that your data scientists or you can basically experiment with different models, different ideas, and work iteratively in workspaces and clusters. Once you get to the point where you have a validated model, clean code, hopefully, you may want to push that to the production. And you have two options here. First is jobs, and the second one is services that allows you to run the standalone clusters and for like online inference in case of services, and for like one-off jobs in terms of Anyscale jobs. So what I'm going to do right now, I just want to very briefly walk you through the clusters option. So this is really fundamental component for Anyscale. Your intention is to run your applications, your ML sessions in a distributed way. So we can have a look at the one running cluster. So I created this one just before our meeting, so I can just go here, and it is now running. This cluster dashboard gives you the high-level overview of your running cluster. So about the cluster panel gives like a high-level information about the status, when it was created, and who created that. And it also, this cluster sits inside the project dedicated to this event. Then you have the resources usage. This particular cluster is the same as you guys have. It is 3 nodes cluster and 2 GPUs. So in total, we have 40 running CPUs. 0 are utilized because this cluster is sitting idle at the moment. I don't run anything, but this is my pool of resources that I can use. There is object store memory, 55 gigabytes, and Ray is using that object store to run, to use it for either like storing batches of data so that these batches can be then sent to the workers during the model training, or like to keep the copies of the data and then move them to the particular workers. We have information about the GPUs. In this case, we have 2 GPUs running, 0 utilized. Again, this is because this cluster is idling at the moment. You have a very large or high degree of control how you want to specify this cluster in terms of AWS instances used to start it. And this is what we call a compute config. So what I did in this particular case, I decided to have one head node, which is high memory, R5, and 2 worker nodes, which have 1 GPU per node. Now, it is really up to you how you want to specify these nodes. Again, you can use multiple different types of worker nodes. So that can be single GPU instance, that can be multiple GPU instance, CPU only instances. It is really up to you how this cluster, how you want this to be constructed. Maybe for one more important note here that might be useful is that in principle, when you start the Ray cluster, even though you set it up to be very large, you start only with the head node. You just don't want to like burn money from the get-go running like 100 GPUs. But once you start evaluating your code on these clusters, you will Ray Autoscaler will spin up more instances to provision resources to your computational job that you are running. Having said that, you can set up the minimal and maximal number of worker nodes for a given type, as you see here. Mm-hmm. So that can be anything between like 0 and a few hundreds. Now, in this particular case, I decided to have the minimal number of nodes set to 2, and the maximal is same. And in this particular case, when I start this cluster, it starts with 3 nodes immediately. That might be useful sometimes when you know that you will like execute some Python scripts that with Ray that will need access to those GPU instances very early. So you may want to decide to just have all that computational resources ready for you from the beginning. And in this case, I decided to go with the on-demand instances. As we discussed before, you can also use spot instances.
So by the way, this is a configuration for the project, right? Not for the cluster.
This is the configuration for the cluster.
Oh, okay, gotcha.
Let me just jump to the configurations.
And before we leave, are there serverless options? Or you have to stand up an instance, like Fargate, something like that.
Yeah. Frankly, I don't know answer to this question. So Kyle, if you know if we can
just put it in the
do
chat.
it, just let us know on chat. If not, we can follow up.
I mean, the only reason I ask is, stand up an instance, it's always expensive, especially these G instances, P instances. They can be $30 an hour. And people accidentally leave them up for months, and then we, have to deal with that all the time. It's always better to run serverless if possible.
Yes, I'm happy that you're mentioning this. So there is two guardrails for you in Anyscale. First one is that you can terminate that after n minutes of inactivity here at the very bottom. So what you see here is essentially the panel that configures and starts your cluster. So if by default this is 120 minutes, so if that cluster is idle for this amount of time, this will be terminated automatically. So you will not be notified during the billing period that you are running some large cluster for last 30 days.
That's good.
And
that's good, but it requires a checkbox. If you, I guess, maybe this is an advanced question, but cost issues come up all the time. Do you have guardrails templates for AWS organizations so you can see who's billing what and limit their spend?
Oh yeah, this is a great question. I believe that.
Yes.
Kyle, can you help me with this one? I don't know, but I believe that Kyle can give you an answer. Again, if not, we will follow up.
It might be nice to follow up because it's going to come up, and a lot of the large customers, the major industrial customers, they use organizations specifically for that purpose. And if you have, and very frequently, like you'll see in finance, you'll see almost every bank is going to be using organizations and limiting access. And the term guardrails sparked the thought because that's specifically what they're called, the ways that you enable and limit cost expenditures on AWS.
Right.
And then you have things like, what is it like? We have like a whole family of partners that do nothing but cost management on AWS. So anyway, it'd be interesting to see, what your story is there, if not solutions.
Yeah.
We don't have to go into that now, but
for sure. Let's follow up on that.
Okay.
Hey, Camille, can you scroll down for a second and show there is a drop down for advanced instance configuration, resources and advanced that section? Yeah, and
this
if you go to
one?
instance, yeah.
Instance config.
Here, okay.
Down at the bottom.
You mean this?
There's a right arrow. Oh, is that it? Because I see advanced configuration at the bottom there. That looks like an arrow.
Yeah, so I think to your point, Chris, if we could pass some ad hoc tags to this instance configuration, then that would automatically show up in CloudWatch, right?
Right. Okay. Yeah, there's many roads to Rome there. It's just, see a checkbox there. Oh, that's good. It's there.
It's luckily it's checked by default.
Right.
So you need to be.
I mean, the number one question we get from every startup that we gave $100,000 of credits to is, how do I get another $100,000? Because the free money they just waste by standing up P3 and just let it go for a month, and then all the money's gone.
Yeah. All right. Let me quickly continue. I think that I will spend a few more minutes on the clusters and workspaces, and then Emmy, I will let you take over. So what we saw previously is one example configuration of the cluster. What you can do, you can configure your cluster in any way you want, meaning that you can have some cluster configurations so these are really, let me just find my particular. Yeah, okay. So the idea here is that once you start the cluster, so these are the instances, and you want to have some particular environment on these nodes. Environment, I mean some libraries for ML, some Debian packages, maybe some environment variables and others. So here, what you can do you can actually save your favorite configuration and reuse it multiple times. You also have a separate view that allows you to create the cluster configuration so that you can manually take like a base Docker image and set it up in a way that fit your particular needs in terms of Python dependencies, environment variables, version of Python, any other packages or software that you need to have on your workers. And the post-build commands is a useful tool that also allows you to like maybe clone the code from the GitHub to this particular worker, to this particular environment, so that you can very quickly start development on the code that you now have like baked into the environment.
So if I know that there are multiple machine learning frameworks support distributed training, for example, TensorFlow or PyTorch. Are they going to configure in here, or is it different?
Yeah, so with Ray, actually to run distributed PyTorch on multiple workers, you just need to use Ray integrations that we have, and that's it. So you don't
they're
need
exclusive of the PyTorch tools.
Yeah, so
Okay.
what PyTorch have is PyTorch distributed module, and this module is responsible for like communication between the replicas of the model, running gradients, averaging, running backpropagation across those replicas and stuff, and run the all reduce step. So we are actually using that PyTorch distributed, and in case you want to run like a PyTorch or PyTorch Lightning on Hugging Face across multiple workers, you just need to use our integration. So we are essentially using Ray, and Ray will make sure that PyTorch distributed processes are started on every worker in your cluster, and that it can like communicate and stuff. So Ray will play the role of the orchestrator.
So it's an additional layer of this physical cluster deployment.
Yeah, so this cluster environment is essentially the Docker image that you will have per worker. So here we are just talking about dependencies, version of Python, maybe environment variables and other things that you need to have per worker. Now if we start this cluster, so every worker indeed has this environment, and we go like one level up to actual Ray application, you use Ray and Hugging Face and others to develop your application that will be run in a distributed way.
Great, thank you.
Sure.
And that's a quick question, sorry.
Yeah.
So for this cluster environment, this always has to be starting from the base Docker image of Anyscale Ray, or let's say,
You can bring your own Docker.
Okay.
Yes.
On top of that, just maybe install the library of Anyscale, right?
Yeah. So you can bring your own Docker, and then you can have your favorite images as an environment.
All right.
Yeah.
Can I do this without this interface and directly do it on AWS Cloud? We
Like,
can, right?
is there an SDK, I think is the question.
This is a good question.
I got one too.
I don't know.
Yeah.
I didn't have the need before. I will follow up with you on that.
Okay.
Yeah.
Thank you.
Sure. Okay. So just to summarize this part related to the clusters.
Kyle just responded online. Yes,
Okay.
they have Anyscale SDK.
Mhm.
Yeah.
Okay.
Okay, great. Thanks, Kyle.
And Terraform. All right.
That's important as well.
Okay, so the few tools that are very useful in the context of the clusters is Jupyter Lab. So this is one sort of default way for quick experimentation and model development. So I have this control here. I just click on that, and that would start the Jupyter Lab in your cluster. This will run on the head node of the Ray cluster, but you can like easily use the whole cluster inside the Jupyter notebooks. Then we have a dashboard. Dashboard is really your entry point to the observability of the cluster, so that I have like bunch of GPUs, how well I am utilizing them during model training. Or when I'm running some training, for example, for the XGBoost models, what is my utilization of the CPUs? You can also observe the object store memory usage. So that observability tool gives you few options. So metrics is to observe infrastructure. Then you have jobs and actors, which I'm not running anything at this moment, but these are the information that you will see when you are doing the model training, for example, or the model fine-tuning. You will have relevant actors that are running certain processes in here. So in this way, when you look at that, you can have a good understanding if your application behaves in the way you want. This is first one. Second, is your infrastructure with like responding in a way that you wanted, including like proper utilization of your infra. Finally, the logs. So Ray and running applications, they produce a lot of logs, and if you need to debug something or you have some errors, you can just jump here, grab these logs, and like go through them and debug.
Or install with and bias, right? And also
Yeah.
check.
It is actually this is like very accurate that for experiment tracking part, working with like weights and biases or MLflow to just have a better visibility how your model training is progressing is like very useful. So actually like Anyscale and weights and biases goes together really well in this case.
Yeah, I would say that they're very complementary, and my mental model of it is that you have your sort of infrastructure component, right? So looking at your GPU utilization, for instance, you have your Ray application component, taking a peek at your tasks, your actors, your active processes, and which nodes are active versus inactive. And then you have your ML application layer, so that's more like experiment tracking. So these are super complementary to each other. You can use weights and biases to, look at your experiments, use the dashboard that's built into Anyscale to have a sense of, am I using the resources that I have effectively?
Yeah. One last thing that I wanted to mention in the context of clusters is that you also have a running terminal, which is basically very useful. And this also allows you during the development stage, if you have like one missing library and you want to quickly install it, you can also do it here. So that when you are developing rapidly, you have some initial or baseline environment, and you can like interactively change that here directly in clusters. All right, now just 3 minutes on workspaces. So workspace is your go-to place for interactive work experimentation with ML models. The biggest difference between the workspaces and clusters that I need to mention now is that when you terminate the cluster and you restart it, that will start from that configuration that you had. So if you did any changes to the code and environment, all these changes are gone, which is not the case with workspaces. With workspaces, what you can do, you can start a cluster and start the workspace. The underlying infra is essentially a cluster, but you can work across multiple sessions. It is really experience where you are working on your local machine like laptop. You are developing some model, trying ideas. You finish your day, you terminate the workspace, you start it the next day, and you start from that state that you left off. So in this way, you can really quickly experiment with multiple ideas. You can actually duplicate or share this workspace. So say I'm working on my batch inference with images, and I actually want Amy to have a look. So she can actually go here, just duplicate it, and she will have the same thing, and she can like work very collaboratively with me.
And is there a dependency between workspaces and projects? In other words, do you need to have projects set up before you could use workspaces?
You don't need to have projects set up. So when you don't set up the project, that will be just a default project. But sort of my recommendation is that assign some sort of bucketing in the work that you are doing, so that you have a separate project that reflects the actual projects that you have in your company.
Okay.
So is that possible? Like say I have like the two project content in the same workspace, and then if I share with colleague A, but he only supposed to know project A, then if she or he copy the entire workspace space, well, she also like know the project B, right? So is that will that be an issue or it can be excluded?
Yeah, so are you saying that, hey, if we have some like permissions per project, and then if people don't see each other projects, and I want to share my workspace with my friends.
Yeah, basically like
project.
Can two project content be stay in the same like workspace, right? So I'm not sure is that kind of
I see. Okay,
right
yeah.
question.
I think I gotcha. So let's have a look at that from the bottom. So we have that sort of fundamental unit, which is a cluster, and you work with clusters. You can like start multiple clusters like every day to do your work.
Yeah.
Now we have a workspaces, and for now, for simplicity, let's say that the backend for workspaces are Anyscale clusters, and this is really workspace for you, like personally.
Right.
So that you can have multiple workspaces if you choose to. You can also use workspaces for like ad hoc work. So you can like quickly start new workspace. It is really just a minute to like provision you with the whole cluster. So you can do some ad hoc work and just terminate it. You can also work with the workspaces across multiple days. But this is just like a single unit with a single cluster attached to it.
Okay.
Yeah. So now within the project, you can have as many workspaces and clusters as you wish. But workspace is mapped to the single project.
Okay.
But you can always start a new one in a different project. There is really no limits in this regard.
Gotcha. Yeah.
Okay, cool. So to summarize this, similarly to clusters, we have Jupyter Lab. You can also launch the local Visual Studio Code. So this is the remote experience. So the vision for workspaces is to enable data scientists, ML practitioners to use like the tools that they are familiar with, like VS Code, my favorite local IDE. And you can actually start the remote session so that you can actually work on your local VS Code, but you have a SSH session to Anyscale so that everything is actually executed on the cluster. So that remote experience is something that, it's worth noting here. All right, having said that, I think that I will conclude for now. I'm happy to take any questions if you have some.
Well, we need to be a little sensitive of time too. I don't know how long Emmy's portion is.
45 minutes.
We
Okay.
still have 15 minutes. 15 minutes, right? 3:45 is the end of the lab.
Yeah.
Yeah, we have 15 minutes.
So if it's 45 minutes and we only have 15 minutes left, we better hustle.
Okay.
Yeah.
Right. Okay.
We can probably go a little over,
We
but
also started a bit late.
we started a bit late. I just
All right, so let me just stop sharing my screen. So I think that for simplicity, Emmy, you can go all the way till the end of the session.
Yeah, sure. No problem. Okay, let me share screen.
Please come up also here so that we
looks like maybe you're already just sharing in Chime.
Yep, sounds good.
Good. Okay.
Great, awesome. So this is the hands-on lab portion.
We're getting a little echo. So
I already muted myself.
but do you have your mic on? Yes? No?
No.
Oh?
I think it's fine now, right?
I don't know. I'm hearing echo. But just keep going. If folks are hearing echo online, just let us know. But please go ahead.
All right, sure. So let's rush through this. I have a lab here to demonstrate mostly Ray, and we're running on Anyscale clusters here. So you'll have the opportunity to use the features that Camille had demonstrated. And to just sort of high-level motivation for what we're doing, we just have a few slides to orient you on the task that we're going to do, which is this distributed model fine-tuning. So just to recap why distribute training at all, right? So this plot is from OpenAI's recent blog on AI and compute, showing that roughly every 3.5 months, the amount of compute required to train the largest models is far outpacing Moore's law. And even if you're doing downstream tasks like starting from pre-trained models, this will affect you. If you're doing hyperparameter tuning, it just compounds the problem. And the design pattern that we're going to be targeting with this lab is data parallelism, not to be confused or conflated with pipeline or tensor or model parallelism. The idea here is that we're going to take a very large data set, shard it into different batches. Those batches will be then fed into different worker nodes that all have a copy of the model on it, along with any sort of pre-processing logic. Those worker nodes are going to be sort of by Ray, and in the back end, you have PyTorch distributed data parallel that is syncing the weights so that once you're out of batches to fine tune and train on, you'll have a fine-tuned model at the end. And so we're really going to be demonstrating Ray AI runtime. So when I talk about Ray, it's this open source Python specific distributed compute framework that's meant to be very general, meant to run on any cloud, meant to be Python native and have these simple APIs that really resonate with machine learning practitioners, data scientists, ML engineers, and so on. And so what Ray AI Runtime is this high-level set of libraries that offer you these simple abstractions that really target different areas of your machine learning workflow, from data preprocessing, training, tuning, serving, reinforcement learning workloads, and so on. And instead of imposing a new standard or having a very opinionated framework that's very picky, it integrates with these really popular machine learning workloads, frameworks so that you can plug these in. And it's really meant to exist in this ecosystem, in this conversation. So specifically in our lab, what we're going to be doing is instructions and demonstrations. So instructions and demonstrations, what is that? An instruction is a prompt or a question. You might have an input, which is additional contextual information, and then your output is your model's generated response. So I have an example right here. So an instruction would be like identify the odd one out. An input might be a list. In this case, it's Twitter, Instagram, and Telegram. And the output is what the model thinks is the answer to the instruction.
I have a question regarding the previous slide. I see you have each step in the ML ops, right? And can those steps integrate with the SageMaker pipeline?
Right, that's an excellent question for Kyle in the chat, and I'll let him take it over just so I can keep rolling. Okay, cool. The model that we're going to be using is Flan T5, which is this variant of the T5 model originally released by Google in 2020, and it's specifically fine-tuned on these instructions, which is the Flan portion of T5. We're going to be taking this from the Hugging Face Hub and fine-tuning it further on the Alpaca dataset. You might have seen the blog released by the Tatsu Lab at Stanford, fine-tuning Llama on Alpaca. This is the dataset. It's 52,000 instructions and demonstrations generated by OpenAI's TextDaVinci. And the goal here is really to get through fine-tuning, but there's bonus material in your lab targeting hyperparameter tuning as well as batch inference. The strength of Ray and Ray Air is really end-to-end machine learning workflows that allow you to have these persistent components so that you don't need to have a different scaling solution for each part of your ML workflow. So you avoid this overhead of stitching together these different solutions. Okay, so with that, you can meet me here. So within your Anyscale cluster, you can open up Jupyter. And it lives in the NLP workloads directory under text generation. And it's called model fine-tuning and batch inference. So I'll show it here as well. So you have NLP workloads, text generation, and then this notebook. And if you have trouble finding it, please ask in the chat, and then our TAs can help. All right, perfect. Let me expand this a little bit further. Okay, so here's our mini roadmap of what we're going to accomplish today. So we're going to be doing some data ingest and pre-processing, fine-tuning Flan T5 on the alpaca data set, and then if time allows, we'll do a hyperparameter tuning loop as well as batch inference. So I'm going to go ahead and get started and set up just some imports and utilities that we're going to need throughout this notebook. In this notebook, you'll see maybe that you don't understand every line of code right away, or there's a bit text-heavy description. For our purposes today, trust that I'll direct your attention to what really matters so that you can hit the ground running. I'm going to jump to this section called initializing array runtime. So I'm going to import array as well as call array.init. When I call array.init, what that does is it initializes array runtime, sets up some communication in the background, and you might have noticed from before when Camille was demonstrating the dashboard, if I go and open this up, since I now have array runtime, I now have a job that's currently running along with metrics here that you see in real time. So cluster utilization as well as the nodes that I have available. So it says 3 right here, since everyone that has a provision cluster with us today for the tutorial has 2 GPUs on 2 nodes as well as a head node, so 3 nodes total. So you can either go to the dashboard in the link that's printed out, or you can, if you're in Anyscale, you can just go to this quick link up top for the dashboard. The dashboard is also available for open source users. So if you're developing locally on your laptop, for instance, or connected to AWS, you would still have access to the dashboard. You need to do a little bit of a manual setup for the Prometheus and Grafana integrations, but it should all be available to you.
Quick question. So
yeah.
this Jupyter notebook running on the cluster?
Yes.
Okay.
Yes.
And then in that sense, all the notebook running on that cluster using the same, let's say, environment library.
So the question was, is everyone who's running Jupyter notebooks in
let's
this
say
cluster?
both you and me running using the same cluster, like your pip install some like will that affect me?
No, so
Okay.
we're on different clusters. So I'm in my own cluster right now, and you would have your own, and there's everyone that's participating has their own. So the environment is sort of contained to me.
Okay.
Yeah. Okay, cool. So we're going to ingest the data. I'm going to set up these utilities really quick. We are fetching the data set from the Hugging Face hub as well. So you have this utility, which is load data set, as well as splitting into training and test. And so you can see it's a data set dict right here with our train as well as our test. Now, I'm going to display some sample data, and this just reinforces your mental model for the task that we're doing. There's some sort of instruction, there is helpful input, sometimes it's blank in case there isn't additional context needed, as well as the output of the pre-trained Flan T5. And then this text column is just a conglomeration of the instruction input and output. So I'm going to now convert this to array data set. So we fetched this from the Hugging Face hub. Now we need to convert it to array data set, which thankfully isn't too difficult. I'm using from my array data library this from Hugging Face to do the conversion, and that runs fairly quickly. Now the question is, like, what is array data set and why are we doing this conversion? Array data sets are the standard way to load and exchange data in Ray Air. They support a number of things, but the ones I want to call out specifically are support for repartitioning or sharding the data set very easily into different batches, as well as batch processing. So applying a certain function to batches of data. That function could be a pre-processing function, which is what we're going to do in this lab. It also could be a model, for instance, if you wanted to map this model onto batches to generate predictions for batch inference, for instance. Okay, scrolling down, I'm going to set up my training and validation data sets, which is a small step, but something I want to call out specifically with what this cell is doing is I have this flag here called small data. It limits the number of samples from the data set I'm using to just a small amount for demonstration purposes. If you have more time to play around with this, feel free to change it to false so that you have access to the whole data set. But because I want to keep this a little truncated, I'm going to keep mine to true. So we arrive at our first sort of distributed step here, which is distributed pre-processing. What we need to do is implement this pre-processing function to apply to our incoming batches of raw natural language data. And the way that we're going to do this is use from the library Ray data a component called batch mapper. And in order for batch mapper to apply a function to batches, it needs to have some sort of function to apply. So what we need to do is, after I import this, define a pre-processing function. Now, there's a lot going on in here that mostly has to do with formatting for what Hugging Face expects, but let me direct your attention to the thing that really matters, which is this tokenizer. If you're unfamiliar with the Hugging Face hub and how these models work, a tokenizer is a component specific to Hugging Face that is associated with each model that ensures that the raw input is in a format that the model will accept. So our tokenizer is specific to this Flan T5 model. Something that I want to call out as well is I'm using this base model for Flan T5. There's a lot of different variants that I've linked in the description in this notebook. The variants range from small to large to extra, extra large, and so on, and they just correspond to how large the model is. Again, I'm using the smallest version here just to speed up things for the demo, but this is another lever that you can pull to really experiment with what Ray can do. So the core of our pre-processing function is applying this tokenizer that takes some sort of natural language, and in this case, maps each word onto a particular ID in our vocabulary for this model, as well as sets up an attention mask, so which words to pay attention to and which not to.
Quick question.
Yeah.
So you convert to the rate data set
Yes.
before doing the tokenization, right? So you convert the data set, and then you do this pre-processing tokenization.
Yes.
Okay.
So right now what we're doing is we're setting up the pre-processing function logic. We're not applying it yet, and I'll point it out specifically when we do this batch mapping, and I'll return to your question so that you have this mental model of what's a Ray data set and what's not.
I'm
so,
just curious
Excel
about.
is pretty important here.
Someone raised a hand.
Oh.
Akko?
Yeah, thank you. Just a curious question. Are you using Ray just to take leverage of distributed computing across multiple GPUs? I mean, couldn't we hypothetically do this with TensorFlow distributed?
Right, that's a great question. So one of the strengths of Ray and Ray Air is end-to-end scalable machine learning. So if you use TensorFlow distributed or PyTorch distributed, that scales your training workflow, but that doesn't necessarily solve when you want to do hyperparameter tuning or batch inference and then serving a model in production, for instance. And so the idea and the strength of Ray Air is to reduce the friction from going from interactive development to production environments, right? So if you are a data scientist and you write your Python application, your ML application, or so on, and that works great in your development environment and you have a flow going, once you go to production, if you have patchwork solutions for your hyper-specific workloads that you're doing at each stage in the MLOps cycle, you're going to introduce a lot of overhead when you're trying to have this go into production with potentially really large data sets or incoming or new models that you need to swap in and out. So short answer is if you are just doing training and fine-tuning, for instance, then maybe you don't need to do Ray. If you are doing more than that, and it affects other parts of this ML lifecycle, then Ray is probably your best bet.
Thank you. That's an amazing answer, because especially because you're trying to do cloud computing across multiple GPUs.
The first question we understood, then it got super garbled. So watch your microphone maybe, or pull it away from your mouth, something. Can you repeat the second part of your question? There we go.
I just wanted to thank for that answer, because in our model, at least from the design, we were concerned about scalability, and I think Ray is an amazing solution. So thanks for giving that clarification. That really helps.
Yep, no problem.
I can also add maybe one more comment here, is that, for example, for PyTorch distributed, like training on multiple GPUs that are on a single workstation is pretty straightforward. So we don't need Ray to distribute that. But once you need to do this step from single workstation to the cluster, things are getting very complicated, and this is the moment when Ray is useful for you.
Yeah, perfect. And it fits very much, I think, much better with the whole Kubernetes landscape. So thanks for clarifying. That really helps.
Right.
Thank you.
Awesome.
So I would like to clarify. Yeah, so you have a drop load, right? And then Ray gonna adjust, scale up and down for what or how many nodes you're gonna have for that distributed training, right? If it's just a single node able to accommodate that kind of training load, that kind of model size, you're still gonna just have one instance running in Ray for supporting that distributed training, right?
For sure. If you have single instance, you can also use Ray, and this will scale up and down within this single instance. Yeah.
Okay.
Right. And that's, one of the sort of forward-looking strengths of using Ray. So I don't need to, first of all, I don't need to be a distributed systems expert. Second, I don't even need a cluster right away. I can just run this on my laptop. If I am at a point, whether I'm a researcher, I'm in industry or wherever, where I'm thinking about, really machine learning systems, right? I might be at the stage currently where I only need one machine. I'm only working on my laptop, right? But in the future, right, if I need to scale up, that, introduces a whole lot of friction points and introduces me to a landscape that I don't know. Because you can use these high-level APIs right away, not concern yourself with the distributed systems aspect of it, there's this seamless infinite laptop feeling where going from your laptop to a cluster, you don't need to change your code if you've already been familiar with Ray and you're like, oh, I got batch mapper, like this is fine, right? So yeah.
Yeah, and especially the whole batch orchestration with a distributed TensorFlow is like really, it's hard to get right. So having something that manages or controls that plane is awesome. Thank you.
Okay, so let's truck along here. So I'm setting up my batch mapper, and I'm passing in my pre-processing function that I've defined above. I just specified that I want my batch format to be pandas, as well as this batch size. It by default is 4096 for this pre-processing. Note that I do have the small data flag on, so I only have 100 samples for my training set. So for these purposes, you will have a batch of 1. But if you're using the entire data set, you will have more meaningful batches. You can meet me in the section that's very exciting called distributed fine-tuning, which is sort of, the main event here. And just as a reminder, in this diagram is the design pattern that we're chasing after, which is this data parallel design pattern. We have our batches of data that we converted to array data set. On each of our worker nodes, we're going to have a copy of this batch preprocessor logic that we just created with batch mapper. So each of our worker nodes is going to understand how to treat that incoming raw data, as well as a model replica. And on the back end, we use PyTorch DDP because we're using Hugging Face here to sync and do the all reduce step. And then at the end, we'll have this fine-tuned model, fine-tuned Flan T5 on the Alpaca data set. So what I need to do first is I need to initialize this training logic for each worker, right? So that each worker knows what to do. So I'm going to go ahead and do my import, as well as set a batch size to be 2. In this case, it's pretty small because the model requires just like a lot for training purposes. And we have access to GPUs, so I'll turn that flag on as well. Now what we're going to do is define this trainer init per worker. Now what that is a Hugging Face Transformers library trainer that we are going to set up on each of our worker nodes, right? And I'll direct your attention to the things that matter the most here. So again, we're using Flan T5. We have our tokenizer, our model that are associated with Flan T5. We also have these training arguments. So if you've worked with Hugging Face before, some of these will look familiar. They're a mixture of hyperparameters as well as different strategies for how to save, how to log, etc. So if you are, in the user's shoes as an ML practitioner, whether you're using Hugging Face or PyTorch or TensorFlow, you'll have your associated parameters that you're familiar with. So this will look very similar. And then what we're going to do is we're going to define this Hugging Face trainer. So this is like sort of in the language of Hugging Face, right? Where you pass in your model, your tokenizer, your relevant data sets along with any sort of training arguments that you might have. And that's all we're doing, is we are initializing this training logic to be placed on each worker. Now that we have that, I'm going to scroll down to define a ray trainer, right? Now, what a ray trainer does is it just wraps around that training logic so that you don't really have to worry about how things are distributing, how orchestration happens, how fault tolerance happens, how memory management happens. Just wraps around, takes in your existing logic, and is sort of a good experience for you. So I'm going to go ahead and run my imports from air as well as train. I have access to 2 GPUs, so num workers is 2. Now let's walk through line by line what's happening here. So we're in the context of Ray now. I'm passing in this trainer init per worker that we just set up. So that's our Hugging Face Transformers library trainer. I have something called a scaling config, which allows me to specify how I want to scale. So I'm setting my number of workers to be the number of workers that I have available, as well as the fact that we are using GPUs. I'm passing in my data sets. These are Ray data sets here, but untokenized Ray data sets, so unpreprocessed. And what you notice here is that I have my batch preprocessor that I set up from before. So hopefully that's a callback to your question. And then a run config, which allows me to set up custom callbacks. In this case, we're defining checkpointing behavior. In the context of Ray and Ray Air, a checkpoint is a saved model. So I want to save, in this case, just the final fine-tuned model. So I can go ahead and set that up. Oh, I did not run this. Okay, awesome. And then we can run fine-tuning. So this will take, if you have all the presets that I do, which you should unless you change something, this will take about 2 minutes. And in that 2 minutes, what we're going to do is we're going to take a look at what's happening. And the best way to take a look at what's happening is through the Ray dashboard. If you are a Ray user, I highly recommend, whether you're using Anyscale or open source, to have the Ray dashboard just open at all times for this observability. Now, I have a job that's running right now, as you can see here, and I'm going to click into this job. And what I see here is some visibility into what my cluster is doing here. So I can take a look at this task progress bar. So I see that some are running, some have finished, and there's other statuses that might crop up here in case you run into an error, for instance, and you might have alerting or failure. You might have statuses like pending node assignment, and you're able to really see what's happening at this granular level. So you can play around with this and look into this. Another thing that's really cool is if I look at my cluster, so if I go to my cluster tab, I see my 3 nodes here. I have my head node as well as my 2 worker nodes with a GPU. And what I can see here is, at a glance, my GPU utilization. And this will sort of, correspond to different steps of the training process. But you're able to see these sort of waves light up as it's going through the different components of the fine-tuning process.
So is this supported by weights and bias?
Right. So, observability is incredibly important, and there's different layers of, observability. And so this Ray dashboard that's specific to Ray is very, very, very excellent at inspecting your Ray application. So your tasks, your actors, your objects, your infrastructure components. Because the old way is just either not knowing in the first place, or relying on error messages, or using command line prompts to look at whether or not an actor has died, for instance. But we have this really nice integration with Prometheus and Grafana for these time series metrics. So you're able to not only see these tasks and actors in real time, but also your Ray resource usage, as well as hardware utilization. So for instance, this would be sort of like, better than canary in a coal mine for whether you're going to run into memory issues, for instance, things that are unexpected. Things don't have to fail in order to be bad, right? You could have performance bottlenecks. You could have things that are just unexpected. You could have tasks that are hanging, for instance, and you want to be alerted to that as soon as possible.
Since Ray is able to auto scale, will it ever give you the error that out of memory when you train large models?
Yes, so I'll give a primary answer and then Camille can add more to it. So yeah, you can definitely run out of memory errors. Let's see. So not observing any right now, which is great. We do have an out of memory killer, which will automatically terminate any sort of process before it, balloons to a bad place, I suppose.
It's because the maximum you set, maybe?
Yeah.
Okay.
Yeah, I think we covered this question.
Okay, cool. Okay. So let me just check in on my fine tuning really quickly, and it's run, which is awesome. And I run this for 4 epochs, something really small for demo purposes. And we can try the fine-tuned model. It won't give you the most amazing result because I fine-tune on 100 samples. But what I'm going to do is the fine-tuned model that Ray spits out is in the form of a checkpoint, and you need to retrieve this model from a checkpoint. In order to do that, you need to pass in what the model expects, for instance. And so this is like kind of a workaround. But we can set up our own instructions and inputs, and we can tokenize them just for this like one-off prediction. There's more in the notebook about batch prediction and how you might want to do this, in a more systematic way. But just for fun, this is what we're going to do. I want to do a time check really quickly. I don't want to go too far past.
Can you support a model parallelism currently?
Yeah, so there's an open source project sort of using Ray. It's called Alpha that supports model parallelism. And then I also have a few examples that deal with using models that don't fit nicely on a single GPU that I can send you. Yeah.
So a quick time check, Chris. How much time do we have? Like,
Sure. Well,
5 more minutes.
it's really up to us. I mean, the folks online are coming from all over the world, and we want to be respectful of their time. But we can go over until you're done. We'll record everything. I'll ask Joe to stop the recording when we're done. That's the only way. The way to do that is just end the call, actually, and then I'll probably edit that a little bit and give it to everyone because tomorrow we have another session, and today's session, we had 75 people here, and there'll probably be folks tomorrow that didn't get the opportunity. So the recording of both yours and Weights and Biases presentation I'll be sending to them. I'll send a link to you as well. And then I hope you're okay distributing the recording.
Oh, for sure.
Okay. If not, just let me know. I'll let you preview on YouTube before I distribute it.
Okay.
I regrettably have to call an Uber now because I won't make my airplane unless I do. But Joe, if you don't mind just ending the session for everyone, you could go as long as you like, as long as Joe likes. Yeah, Joe's the captain of the ship.
Okay.
So they're the guests. This is very interesting. Let's keep going.
And I have to say, I mean, we're getting comments here, some people are just saying that this session today was just extraordinary. Weights and Biases, Mario's, yours. It's really a powerful session. Just the fact that 600 people signed up still kind of blows my mind. But so you're getting kudos in real time here, and we'll collect our ratings and when it's all over and share that with you as well in comments for improvement.
Okay. So maybe, Amy, on our side, to keep people too long, maybe we can skip HPO, do the batch inference, and then like the last slide of our
Okay, sure. Sounds good. So I do have a section on distributed hyperparameter tuning. TLDR, it's just fine tuning again and again with different hyperparameters. So you can do that. I'm going to jump down to my section on distributed batch inference. So what is batch inference in this context? So we're going to run prediction at scale. So what we just played around with was like a one-off prediction using our model for our own personal fun. What we want to do is inference and generating predictions on large volumes of data. Now, I know that in the world of MLOps, there's sort of this like offline batch prediction as well as online batch prediction. The one that you're going to see here is offline, so using like already existing data. We're not streaming in like
I'm going to
new.
excuse myself.
Yeah, of course.
Thank you again very, very much, and let's all do this again in San Francisco.
Sounds good.
Cheers.
And next slide.
All right, awesome.
Oh,
So,
let's do it again in Singapore.
Even better.
Even better.
So this is our flow that we're going to work with right now, which is taking in these batches of data. There's this component that you can use in Ray Air called a batch predictor, which takes in as input a predictor that holds all the prediction logic as well as distributes that, as well as a checkpoint object. So the checkpoint, again, is a saved model that will apply to each of these batches, and then you can generate predictions. So what I'm going to do is I'm going to import my predictor as well as my batch predictor, and then I'm going to set up a custom Hugging Face model predictor that's fit to my particular model. Now there's quite a bit going on here, and a lot of it is just to make sure that everything conforms to what the Hugging Face model expects. But let me direct your attention to what matters here. So we're specifying our model as well as our tokenizer and whether or not we're using GPUs in the initialization. We have this method called fromCheckpoint, which creates this Hugging Face model predictor from our saved model, and just ensures that the incoming batches are treated nicely in case they're raw input text versus already pre-tokenized text. So you can have a mixture here. And then we have this function here, predict NumPy, which actually does the prediction, takes the incoming data, tokenizes it if it's not already, and then returns that output after the model is applied to it in this nice pandas data frame. T5 is an encoder-decoder model, so you'll see that you have to do some decoding to be able to read it with your human brain. And then I'm going to set up my batch predictor from a checkpoint. So I'm gathering my fine-tuned model that I've just fine-tuned on Alpaca from this checkpoint. My predictor class is the custom one that I just implemented above, which is the Hugging Face model predictor. I have my model class as well as my tokenizer, whether or not I'm using GPUs, as well as a few other ones. And then I can go ahead and run batch inference. So I'm going to call .predict. I don't have a new test set here because I wanted you to be able to see the difference between the generated output and what the original output was in the validation set. So I'm passing in my validation set again here. Num GPUs per worker is just going to be 1 GPU per worker node here, as well as the batch size. And I have my small data flag on again, so I'm only generating 100. And then this max new tokens you can set to ensure that all of these input text is truncated to whatever length that you specify. So I'm going to run prediction here. And anytime you do one of these long-running processes in Ray, I highly recommend that you look at the dashboard, see what's going on, are my GPUs being utilized, right? This is a relatively quick task for prediction. So I'll just go ahead and run the second cell, which is just taking a look at our predictions. And what I'm doing here is I'm taking my validation data set and displaying that along with what our newly fine-tuned model outputs. So as you can see here, these first 4 columns are from the validation data set, and then our generated output is what our bespoke fine-tuned model outputs here. So that's batch inference. There's quite a bit more that you can do with Ray. Of course, there's the hyperparameter tuning step. There's also, you can do distributed data ingest, you can do model serving, you can do reinforcement learning workloads. I've really scratched the surface of what you're able to do with Ray, but hopefully this gave you a taste. Yeah.
So can we also define the output, location, and then we just ready to run, for example, S3L?
Yeah. So you can, since it's a Ray data set, you can save and change the file format and location to save your outputs.
I have a question because for the inference step, performance is very important, right?
Yes.
Like response latency and stuff. is it possible that the user define, I would like to this kind of a performance and please scale for me during the inference time?
Yeah, that's an excellent question. We have a few engineers that work on that specifically that can answer in chat, but my first response is the pattern that you see implemented here is, really offline batch inference. So you don't really sort of see like, what real-time inference would look like. And we have a few examples that we can send you for how to optimize that.
Wonderful, because many customers ask that.
Yeah.
Also,
Thank you.
one, to add more color to this answer, when we considering online inference, Ray Serve, so there is a library specifically for serving, it offers this model replica feature, meaning that you can set it up to multiple replicas, so if you have more traffic, it will be distributed across these replicas. And scaling this up and down is supported by Ray.
Yeah, of course, we need ways and buyers to tell us where is the bottleneck for inference, real-time inference. Thank you.
All right, so the last thing that I have is just like for anyone that's watching either synchronously or asynchronously, we have a bit of a feedback survey. We also are raffling off Ray Summit tickets to people that finish the survey, so if you're interested in that, you can go ahead to bit.ly/Anyscale Ray feedback. And we'll stick around for questions.
Yeah, I think that we concluded. Thank you so much, Amy. So again, this survey is really for us, so it is really optional. If you want to help us improve over time, please fill out the survey, and we will have this random draw from survey submissions, and we award 3 people with Ray Summit ticket in September.
Yeah, could you post that survey link on the chat?
Yes.
Yeah.
And that's really it. Thank you so much.